And I can tell you that the most difficult part and most time-consuming part in my experience, and that's based on a couple of workshops where we try to integrate nanobioscience into undergraduate curriculum in existing courses. The most complicated part is to make that information meaningful. Just because I have a set of slides doesn't mean I know what to say. It's as simple as that or as complicated as it gets. What do I say? What are my talking points? To say you have Geology 300. You have a teacher. We would like to immerse computational methods into that community. What does that teacher say? If that teacher says this is useless, we don't have to continue because we have not done ourselves a favor. We have to provide that person with the ability to bring that into their classroom in a context that is fair to the field and helps us. So I think we have to make the effort to provide that. And I will show you one example from a different context, what I think that could look like, but this is a lot of work. So this is one of the bottlenecks. It always sounds great, but you have to find somebody who also does that. So what we came up with in that context was sort of a two-tier approach, fairly cheap. The first one is simply give us what you have. We take anything and everything you have on this particular topic. In this case, it was nanobioscience. We collected about 400 slides, which is half a course roughly. And that was completely annotated, not annotated. So you have to spend another 1.5 days or get these people to annotate it. And that's what the next step is. But I think we have to have something like, they got $200, I think, simply for providing something, and then they're going to get another fee or so for actually helping us to annotate it. But I think it's important to keep in mind to make these things meaningful. And so here's one example. This is something I used in a nanoscience course, was it 2 years ago maybe? And it was under introducing why quantum mechanics is important. This is at the undergraduate level. We should not forget that. So this is why there's almost no formulas probably in a physics department. It's very conceptual. But really all it is you have the electron, the proton, you talk about these, and you say, well, what should happen? Classically, what happens is they get together, they annihilate, and there's a big flash of light, and nobody's here to ask the question, what happened? So this is when the students get really puzzled, because of course they know something is wrong with that picture. And so you start thinking, well, how long does it take? So that's usually a question that comes up. Well, maybe that takes a long time, billions of years. And the answer is no. It takes about 10 nanoseconds. And we should not be here. There's a flash of light. And each time we pop up from the quantum foam, we are gone again. So this is one part. This is one slide. But then in order to make it meaningful, I thought, here is a few talking points, what could be said in this context. Now, this is not saying that you have to say that, but it gives you a list of options. If you would like to change it, it gives you a starting point, what maybe to think about. And then finally, something that is very important these days to NSF in particular is student activities. What do you do with it? And then also the other thing that we learned the hard way is you have to think about assessment. If you can assess that stuff, NSF will love that. But the assessment, at least I have not been trained in assessment, and so it's very difficult to come up with something that's meaningful. You can assess, and the numbers demonstrate something, some sort of progress. And so these are some of the aspects. Again, this is not meant. This is one example, and not meant as a must. Of course, existing efforts is always worthwhile to look at those. David Mock gave a talk a year ago at Compress. And we invited him afterwards to talk at some of our workshops. And yes, he talked about meta tags, how to make it searchable. All the fancy stuff. Again, we're going to reach the same problem. Who does it? And on what time? Summer schools, short courses, we talked about those. Integrative, maybe it's worthwhile thinking about some bigger picture, like CIG, combining something like a computational geophysics summer school, like CIDR, but the computational equivalent to that. Would that be possible? Because it would engage a larger part of the community, and we could probably look at the CIG model, and then the analysis tools. I think some of the analysis tools would be good to provide some initial analysis tools. I think PWSCF may provide that with the web interface, but something like that would be good to help students in particular who are not regular practitioners of these techniques to make sure that they extract sort of the correct information from these files. So a lot of that is logistic, and obviously I don't have perfect answers for any of that, but it's just a few reflections on what may be good ideas. How to make that happen is a different issue. In summary, so I have moved towards DE, that's energy and environmental applications of density functional theory. The goal in the end is to do ab initio electrochemistry or redox chemistry. That's activation barriers, that is building fuel cells, and guidance to industry, basically, how to make these catalysts more effective, what are promising routes. Materials optimization, that's really what it is, and then I have had some ideas for community development. And with that, I would like to thank you and be open for any questions. Oh, I will be known in the end for some education. That's fine. That's fine. I think it's important. It's very important. Dane?
I just had a broad question. Maybe this is for later discussion, but you brought up a number of areas where we might be focusing. Is it worth, given that we're thinking of a relatively small resource here, trying to decide which community we really want to serve? For example, if we really want to help develop educational materials for non-specialists in computation to help train them, I think that's great, and that might use all our resources, and that should be the focus. Or do we want to be developing resources for people who are already in the community and are experts and need super high computing and and computing and things like that? And maybe it'd be worth trying to decide which we're going to target, because we may not be able to.
It's in my if I can say a few things, in my experience, for the undergrad or graduate, the teaching materials, sort of like teaching modules that you can use in existing classes, and I passed some on to Edwin yesterday, some of these modules that we have been using, that does not take a lot of time because we already have them. So that is really building a repository, like Compress could house a repository of tutorials for computational material science or mineral physics. You can just download it basically at your own, or you have a webcast or something like that. That you could have. That's not that much effort, it turns out. The real stumbling block is to make it meaningful. That's what we are experiencing. So I think we need to do it in parallel. That's in my impression. Make sure that the future decision makers know about computational methods, as well as have the experts who can carry out cutting edge research.